Hello again everybody, and welcome back. This is the third video in the Atmel microcontroller programming series, and in the first two videos we took a look at, well, the first video was just the first programming and blinking a LED, and then the second video we took a look at changing the clock speed by setting the fuse bits. And in this video we're going to round out sort of the basics part of the series by taking a digital input from a switch, and then we're also going to cover bit manipulations in C. So some of those statements from the first two videos, manipulating bits with logical operators, if those didn't make a whole lot of sense, in this video we're going to cover that, and hopefully that'll kind of round everything out as we move into some of the more intermediate videos in the next steps. So let's go ahead and implement the project that we're going to do today. So GitHub, microcontrollers, and more, and then take out the space, and then there we go, choose that. And then we're going to go to repositories, and then we're going to go to Atmel Programming Tutorial 3-bit Manipulation and Digital Inputs. And then we're going to go to, well, first let's take a look at the circuit here. So digital input circuit.png, and this is the circuit that we're going to be breadboarding today. And the only difference between this circuit and the circuit in the previous two videos is that you'll note we went back to the internal clock at the end of the last video, so there's no more external clock here. And in this video we're adding a switch on pin 4, and there's actually an internal pull-up resistor inside the ATmega 328P, so we don't need to add an external pull-up resistor here. We'll get into that in more detail later. So let's go ahead and breadboard this circuit here. So PD2, which is pin 4. So we're going to grab a jumper wire, count down 4 here, so 1, 2, 3, and 4, and we'll place this over here. Okay, that'll work pretty well, making sure that I got that in pin 4, 1, 2, 3, 4, yep, okay, and then we can go ahead and place our switch here. I'm using a tack switch for this example here, but you can use any kind of switch you have handy, slide switch, whatever you like, bigger switch, smaller switch, doesn't really make a difference. And then we're going to simply ground the other side, and there we go, that's all in place nicely. And again, other than that, it's the same circuit as in the previous two videos. So since the program from the previous video is still in there, the LED's already flashing, but that's okay, we'll remedy that in a moment. So now our circuit's done, so we're going to go ahead and fire up Atmel Studio, and while we're waiting for that, we'll go to the program that we're going to do today. So we'll go ahead and build the project first, and then we'll take a look at what it's doing in more detail. So we're looking for digital inputs.c here, so then we're going to choose raw, and I'm going to move this over to the other screen to copy and paste out of, so we can close out of here, and then new project, and I'll copy and paste the name from the other screen here. And there we go, GCC, C executable, digital inputs, okay. And we're using the 328P. Double click on that and wait for it to pop up. And in case you're wondering, it's very easy to change the name of your main program here. You simply can right click on main.c and then choose rename and paste in the same name there. And then we'll do Control A, Control C from the other screen, Control A, Control V, Control M, Control P. And of course, okay, just double checking I had the battery connected there. So if we choose save and Control F5, it's going to ask us to pick a programmer because we didn't do that yet, so that's fine, we'll do that. Continue, and then we're going to choose Atmel ICE and ISP and Control F5 again, and you'll notice the LED went out, and now if we press the switch, the LED goes on, hold off the switch, it's off, on, off, and then we can do it pretty quickly and it's going to respond nicely, so you get the idea. So that was successful. Okay, so I just paused the recording there for a moment to turn off the picture-in-picture. I don't think that'll be necessary for the rest of the tutorial today. So as I've mentioned in the previous two videos, if you don't have a hardware-oriented background or a hardware-software interfacing background, statements such as this and this and this here, these might not be especially clear. So what we're going to do today is we're going to dive into those in some more detail. And before we take a look at those in code, I made some documents here in this repository to attempt to kind of clarify some of this. So let's see, we have Atmel internal pull-up resistor.png. We'll get to that momentarily, and then probably we'll start with this here, Atmel AVRC, the 3 most common registers explained. And then we have also a bit manipulation cheat sheet, we'll get to that, and then C microcontroller bit manipulations explained. So let's start with Atmel AVRC, the 3 most common registers. and then we're going to choose raw and open, and there we go. So I'm going to go ahead and pull this over. Okay, so in Atmel AVRC there are three for each port, there are three registers that are used especially commonly. Pretty much every program you're going to use at least one of these, if not two or even three of them. And that's the DDR registers, which are commonly referred to as DDRX. So you have DDR B, DDRC, and DDRD with the AT Mega 328P. So some other Atmel chips might have DDRA or DDREF, etc. But the 328P just has ports B, C, and D. And then we also have the registers port B, port C, and port D, or port X. And then we have pin B, pin C, and pin D, or we can collectively refer to those as pin X. So what do these registers do? DDRX is short for data direction register. And each bit of the data direction register for each of the three DDRs controls if the corresponding pin is going to be input or output. And then for port X, if the corresponding DDR pin is set for input, then setting the corresponding port X bit to a 1 will activate the internal pull-up resistor that I mentioned momentarily earlier. We'll take a look at that a little bit more momentarily. And then if the port X is set to a 0, then the corresponding bit will not use the internal pull-up resistor. If DDRX is set to, the corresponding DDRX pin is set to output, and then we clear the corresponding port X bit, that will set the output low at that pin, or if we set the corresponding port X bit, that will set the output high. And pin X is a read-only register that's used to check the state of the corresponding pin. So this is kind of an explanation that's more or less out of the data sheet, and it's maybe not especially clear. So let's take an example, and we might as well use the example of digitalinputs.c that we did today to go through this. So let's say for port D bit 2, actually let's pull up the pinout from the first tutorial. Let's see, here we are, pinout, and then raw, and then open. So recall that we set our switch on pin 4 here, that's PD2, and then we set our LED on PC5, which is pin 28. So if you were looking at the chip, you would probably first figure, well, okay, we'd like to use pin 4 for input and pin 28 for output. So then the next thing you would do is you would look which port and which bit did those correspond to. So then you would see PD2 here in PC5. Okay, so knowing that, then you would do the following. To set port D bit 2, i.e. PD2, which is physically pin 4 to input, you're going to clear the DDR, again that's data direction register, bit 2, which will set PD2 or pin 4 to input. Okay, then you're going to set port D bit 2 to set PD2, which of course is physically pin 4, to set the internal pull-up resistor. That way you don't have to put an additional pull-up resistor on your board. As you saw, all we had to do was put the switch on the board. And then you're going to have an if statement that's going to check the state of pin D bit 2. And remember, we have an internal pull-up resistor configuration here, so this is going to be logic low. In other words, 1 will be the switch will not be pressed, and 0 will be the switch will be pressed. And then if we'd like to set port C pin 5, which is PC5 or physical pin 28 to output, we're going to set DDRC, that's again data direction register C, bit 5, and that's going to set PC5 or pin 28 for output. Then we're going to clear port C bit 5, that should say bit 5 there, sorry, it's an error on my part, I'll go ahead and fix that momentarily. But anyhow, we're going to clear port C bit 5 if we'd like to set PC5 or pin 28 low, and we're going to set port C bit 5 if we'd like to set PC5 or pin 28 high. So again, this is still rather abstract, so I made another document here which hopefully will explain that a little bit more if you're not especially familiar with bit manipulations. So we're going to jump back to the third tutorial here, Atmel Programming Tutorial 3, Bit Manipulation and Digital Inputs, and then we're going to take a look at let's see, we just looked at the 3 most common registers explained, so next we're going to take a look at C microcontroller bit manipulations explained.pdf, and then choose raw and open. And here we are. So let's say that we'd like to do what this statement here is saying. We'd like to set port C pin PC5 for output. So let's break this down, and we can start with the DDRC and the PC5. So if we search through the dependencies in here, if you look through these, you would find in the dependencies that PC5, can go ahead and highlight this. PC5 is defined in the dependencies to be 5. So in other words, and then of course this operator here, bitwise OR, and then equal sign, that breaks down to DDRC is assigned DDRC bitwise OR, and then whatever you have on the right side of this operator. So in other words, we can simplify this statement as follows. We can say that this statement effectively means DDRC is assigned DDRC bitwise OR 1 and then bit shift to the left by 5 positions. Okay, so let's next take a look at 1 and then bit shift to the left 5. So if we write the number 1 out as though it's 8 bits in base 2, we would have this. So 7 zeros and then a 1. And then that's what this 1 here is indicating. So then the double arrow to the left and then 5, that's indicating a bit shift left to the 5. So if we take the number 1 here and then we shift that 1 bit to the left by 5, then we get this. So 0, 0, 1 and then 5 zeros. So in other words, 1 and then bit shift to the left 5 equals this here, 0, 0, 1 and then 5 zeros. So before we get back to registers, let's do a quick review of our bitwise operator basics. So if we have anything, x here is a variable that we don't know what it is. So if we have anything bitwise OR and then 0, that gives us x. Anything bitwise OR with a 1 gives us 1. And anything bitwise AND with a 0 gives us 0, so that clears x in other words. And anything and a bitwise AND with 1 gives us what we had to begin with. If this isn't clear to you, please consult another source on the internet. It's pretty easy to find a quick bit manipulation review. You could start with Wikipedia, but probably most people watching this video are already familiar with this, so to keep the video to a reasonable length, I'd rather not take any more time for that. So continuing on, we also want to remember the tilde character in C is a bitwise not. Okay, so now let's get back to registers. So keeping in mind what we had here, if we can say DDRC contains 8 bits that we don't know what they are currently, but we'd like to set the 5th bit, then we can bitwise OR with this mask here, 2 zeros, a 1, and then 5 zeros, which again is what we got by doing 1 and then bit shift to the left by 5. And then that's going to make a DDRC equal the following. 2 that we don't know, but they're whatever they were before, and then a 1, and then 5 positions that were what they were before. So now if we put all this together, we can break down the original statement. So DDRC is incremented by DDRC bitwise OR with 1 bit shifted to the left by 5. So we can break out this operator here into assignment and then the bitwise OR separately, and then we can simply replace, as we did in our, as we mentioned in here in the dependencies, effectively what the compiler does is it replaces PC5 with the number 5. And then we can simply write out the number 1 as 7 zeros and then a 1, so that's 1 in base 2 across 8 bits. And then we can apply this bit shift to the left by 5, which then gives us this. So now at this point we're bitwise ORing DDRC with this mask here, which is what we did up here. And so sure enough, we're going to get the result that this is what we started with. This is our bitwise OR mask, and then this is our result. So we will have set the 5th bit, and again you start counting at the right. So this is the 0th bit, 1st bit, 2nd bit, 3rd bit, 4th bit, 5th bit. So we will have set, no matter what the 5th bit was to begin with, we'll have set it to 1, and all the other bits will have left them however they were. So we succeeded in what we were originally trying to do. We set the 5th bit, but we didn't change any of the others. So we can use a bitwise AND in a similar manner to clear bits. So for example, in the program that we just ran, so let's go back here. So here's an example of where we set the data direction register C for pin PC5. So that's a statement we just broke down. So now we're going to break down this statement here, DDRD, and then we're going to clear DDRD bit 2, which is what we were doing here to clear DDRD bit 2, which sets PD2, that is pin 4 for input. So if we start breaking this down in the similar manner here, so if we break out this operator here to be an assignment statement and then the bitwise and then we can simply say that the compiler is going to replace PD2 with the number 2, and then we can write out the 1 as this number here, which is 1 in base 2, just with the 7 zeros in front of it, so that's occupying 8 bits, and then we apply the bit shift to the left by 2, and that gives us this, and then we apply the not operator, and that gives us this, And referring back to what we considered up here, if we logical and our 8 bits, which we don't know what they were before, actually in this simple of a program, these registers are they default to 0. So at this point in the program, when it starts, they're 0. So we, in a sense, we do know what the data direction registers are ahead of time, but it's better not to assume that. We want to practice the statements as though these were in the middle of, say, a 500-line program where we might not have known what the register was beforehand. So the idea here is that we only want to change bit 2. So we start with these 8 bits where we're sort of supposing we don't know what they are ahead of time, and then we're bitwise anding them with this mask that we built here, and that's going to clear the second bit, and it's going to leave the other 7 how they were to begin with. So we've succeeded in clearing the second bit and leaving all the others alone. And you'll find that you can essentially do a similar pattern to toggle bits. So first, if we have a quick review of an XOR truth table, so you have 0 and 0, or rather 0 XOR 0 is 0, and then if either one of them is true, you get a 1, and if they're both true, that gives you a 0. So in other words, if we consider that in this way, if you have something, be it a 0 or a 1, either way, and you XOR it with 0, then you're going to get a 0, which you started with, and then a 1 when you started with the 1. So in other words, if you start with anything XOR 0, you end up with the anything. And similarly, if you XOR with 1, you're going to find that it inverts it. So if we have 0 XOR 1, then we end up with 1. If we have 1 XOR 1, then we end up with a 0. So sure enough, it inverted it. So if we say we start with x and then XOR 1, then we get y, where y is just the inverse of x, or x toggled. So now we can evaluate the expression from the first tutorial in the series, and I'll just bring that up momentarily, where we toggled a bit, you may recall. Let's see, here we go. In my Atmel blink.c, so referring to this statement here where we were toggling the lead on PC5. So now we can take a look at that and explain it. So here's what we did, is this line here to begin with. So if we break out this operator here into a separate assignment and a bitwise XOR, and then we simply replace PC5 with 5 just as the compiler would do, then we write out 1 in an 8-digit base 2 number, and then we apply the bit shift to the left by 5. That gives us this. And we'll find that if port C contains something we don't know ahead of time to begin with, and then we bitwise XOR it with this mask here that we've built, that we're going to have inverted the 5th bit, and we will have left the other 7 just how they were. So we have successfully toggled the 5th bit without changing any of the others. And you can apply the same logic to conditionals. And that's exactly what we did in the program that we just did here, is we did if the bit is clear, and remember, because of using a pull-up resistor, the logic is it's logic low, so the button is if it's 0, the button's pressed. If it's 1, the button is not pressed. So, and what we're doing is we're using these macros up here because personally I find that's a little bit more readable. We'll get to that momentarily in the cheat sheet. But in any case, what we're doing here is we're checking if the bit is clear and if the bit is set. So if we were to do that without the macros, here's how it would look. We could do if pin D and then bitwise and with 1 bit shifted to the left by PD2, which happens to evaluate to 2, and then we can simply write out the 1 as follows there, and then if we apply the bit shift to that, that gives us this mask, and we'll find if we'll do the pin D register with that, bitwise ANDed, then pin D ahead of time we don't necessarily know what it is, but if we bitwise AND it with this, then that's going to give us, that's going to clear all the bits except for the second, which is going to leave the second bit whatever it was before. And recall that in C, if you have an if statement that looks at this, if x happens to be 0, then of course the whole thing is going to be 0, and that's going to evaluate to false. And if x is a 1 in any of these positions, it doesn't matter what positive number you have, 1, 2, 4, etc., whatever it may be, that's going to evaluate to true in C. So we can simply feed the result of this statement right into an if, as we're doing here. And also notice that because this is assignment, this is not assignment, rather. Assignment is not used here, so we're not actually changing pin D, we're just checking it. Okay, I had to pause there for just a moment to grab a sip of water, but continuing on here. So now that we have figured out we can check if a bit is set with this statement here that we've evaluated, to check if a bit is clear, we can simply take that same statement and put an additional set of brackets around it, and then use the not operator to invert the result, and then that way we can check if something is clear. And as I mentioned earlier, those macros, personally I find those to be very handy, because if you're reading a long program and you see a statement like this, if you have a good comment, it's clear what it's doing, but just looking at the statement itself, it's not necessarily clear. So personally, I recommend putting these two macros here at the top of your program. Bit is set and bit is clear, and those basically just do these very same things here, but in a macro. So we can simply say if bit is set or if bit is clear. And I should mention Atmel Studio has predefined macros. Bit is set in lowercase and bit is clear in lowercase. Personally, I still suggest using these two or making your own if you prefer a slightly different one, for two reasons. One is the predefined macros are in lowercase, which, if you look at this, it looks like a function, which if you're reading a long program and trying to kind of work your way through it, thought process wise, it can be very misleading. And the second reason that I recommend using your own macros is if you have them, your own macros, you can change what they're doing. You know exactly where they are and what they're doing. And if there's ever a future change to the Atmel compiler, your macros will still remain how they are. So personally, I recommend having your own, although you can use the predefined macros for bit is set and bit is clear if you'd like. So that completes the basics of bit manipulations in microcontroller C. So we have, I believe it was only one remaining document, or actually two remaining documents to take a look at. So we'll go back to the third tutorial that we're currently doing, Atmel Programming Tutorial 3, Bit Manipulation and Digital Inputs. Okay, first let's take a quick look at Atmel Internal Pull-Up Resistor. So as we mentioned earlier, go ahead and do raw so it's a little bit bigger. If you clear DDRD bit 2 to set pin PD2, or physical pin 4 to input, and then you set port D bit 2, the chip will configure an internal pull-up resistor, as we mentioned. So here's essentially the configuration that the chip does if you set the registers that way. And this is extremely convenient because you might be used to, say, another microcontroller or a different circuit setup where you'd have to put a pull-up resistor out here externally. Here you don't have to do that. It's inside here, and then the ATmega 328P senses voltage for you on the pin, and so all you have to do is drop the switch in here and ground it, and you're good to go. So that's all we did on our circuit today. And to sort of summarize some of this, I've made this bit manipulation cheat sheet. So as you're going to future projects, you're probably not going to read this explanation sheet or the 3 common registers explained. You're probably just going to look at example programs for those. But this bit manipulation cheat sheet is pretty handy, and this is something you might find yourself referring to quite often. I still refer to this myself. So basically, this is sort of a condensed version of that bit manipulations explain sheet. So in these examples here, register X that's not an actual register. I'm just using that as an example name. That could be DDRB, port C, whichever register you're trying to set. And then the one here is, of course, starting with 1, as we explained when we broke all those statements out, and then the 3 and 5, and then I think later on I used 7 as well. There's no special significance to those. I'm just using those for example bits that you might want to set. So as we kind of reason through in that manipulations explain sheet, here are some quick examples you can copy and paste in of setting a bit, clearing a bit, and toggling a bit. And then you can even use macros for those if you like. Here they are, if you'd like to copy and paste those in at the top of your program. I don't think it's necessary though. Once you get comfortable with microcontroller C, looking at these statements is pretty straightforward. And then for conditionals, here's how you can do them without the macros. Here's how you could do multiple checks in one line. And then these here are the macros that are personally, I recommend, I'd say this is a good idea to just copy and paste these into the top of your program, and then you can do bit is set and bit is clear very easily. So that completes this video, and in the next video we're going to take a look at analog to digital conversion. So see everybody in the next one.